And a very good afternoon on behalf of everybody associated with the NADP Program Office and the Central Analytical Laboratory. Welcome to our continuing series of webinars this afternoon entitled You and Your Solar Panel. My name is Jeffrey Pribble. I'm Site Support. I'll be joined this afternoon by the Director of the Central Analytical Laboratory, Dr. Chris Lehman, as well as my engineer, Brian Kirshner, the Assistant Database Manager for the project. And if this is the first time you've had an opportunity to join us in our continuing series, pretty laid back. We tried to pass on information related to protocol. If it is the first time that you've joined us, you can refer back to past webinars by going to the goillinois.edu/NADP training that you'll see on the cover page of this afternoon's webinar. If throughout this you have any questions in regards, go ahead and ask the question. What we'll do is repeat it, and then we'll try to answer it to the best of our ability. And like I said, real impromptu, so hope that you learn lots of information and progress from there. Go to our first slide if we could today. Want to do an overview on general. Most of the information that we provide as in our webinars is actual protocol for doing things within the project. This afternoon, what we wanted to do is just kind of give you an oversight of another option related to power away from AC power, the voltage, or straight DC. This is a combination and something that we've actually done at one of our sites within the network, our home site, Illinois 11. We called in a project for some time ago called Going Green. So the overview this afternoon will be solar powered NADP equipment, the sizing panels and battery banks. We'll give you some wiring diagrams, go about some equipment installation, the maintenance of that equipment, and if you have problems with that equipment, troubleshooting as well.
And this is Chris Lehman here. Appreciate that, Jeffrey, the introduction. Just want to mention that we've structured this as a general overview. A lot of the recommendations we make might be specific to your site, your particular installation. So feel free to ask questions through this if you have particular concerns. But we've intended this as a general overview for those that aren't familiar with DC or solar-powered systems.
Yes, as Chris was saying, what may be good for the goose may not necessarily be good for the gander as far as, you know, what would work at one site in comparison with another site. So just a good overview. Next slide, please. The two different collectors that we have within the NTN network are the Aerochem collector and the Incon collector, the two bucket system, the old Aerochem collector, and the new one equipped with an optical sensor called the Incon. How does the solar panel related to these particular two components? For the Aerochem collector, you can run it off of the 120 volt AC line power as well as the 12 volt DC battery power. The Incon, on the other hand, can only operate on a 120 volt AC line. The reason being is because of the sensor involved in this, the sensor on this one bucket collector has a constant draw. And when you hook up the solar system as well as the batteries and stuff like that, having a constant draw will draw away from the battery capacity and cause problems with the function of the collector. So that's something that's currently being investigated within the project. Next slide, please. We get to the Aerochem collector. This has been around since the inception of the project back in 1979. This is what went about. Pretty simple system that actually has the ability to two different setups. As we said in the earlier slide, the Aerochem motor box is designed to work for both 120 volts AC as well as 12 volts DC power, and as well as if you wanted to hook it through a solar system. If you'd see the diagram to the right in the two pictures we have, it gives you a description as to what these the face of the motor box looks like. What is a good thing to know about this is the fuse that runs the DC or the AC that you see on the left and the fuse that's on the AC side, the 12 volt DC fuse, they're kind of they're 1/2 amp to 2 amp slow burn fuses. So if you were to lose one, you can switch them back and forth, and it would still operate the motor box. Next slide, please. Two different rain gauges that we use. Well, actually 3 if you count the Belfort, which is the old chart rain gauge. We have the hot pluvio rain gauge. That requires AC to operate the pluvio. The ETI NOAA 4 rain gauge, on the other hand, can operate with the 12-volt DC battery or the 120-volt AC line power. So we have an option to do both with that. With the optical sensor inside of the rain gauge itself, needs a little less power. Next slide, please. Requirements for good and safe DC. What we always preach is to have, safety in all that you do and where you do it. We want you to be safe. So we have a couple guidelines we highlight in red. One of the things that we always want to preach is, the wiring, proper system grounding, power disconnect, fuses, circuit breakers, sufficient solar power generation capacity. You never want to use something that is necessarily overpowered with smaller wiring, or something that's less with bigger wiring can cause actual problems and jeopardize the safety of the person working with that piece of equipment. Properly oriented solar panels, adequate sized power cables, and proper wiring connections. Want to make sure you have sufficient battery capacity and properly maintained batteries. These are going to be things that we all cover throughout our webinar this afternoon. I'm going to let Chris talk a little bit about the typical NADP power requirements, prices, consumption, stuff like that.
Basically, to summarize, what it's talking about is that the ACM collector has an appreciable power draw. The sensor on it has a constant draw state of about 0.05 of an amp. That's at 12 volts DC. When it's cold, that's below approximately 40 degrees Fahrenheit or sub-freezing weather. The sensor heater turns on, and that's to melt any snow that falls on it. It also heats during precipitation events to dry the sensor, so we don't have the collector open for extended periods. Those are cumulative, so the maximum power draw of the collector is about 1.15 amps at 12 volts in the winter when activated. That's a fairly appreciable power draw, so it confronts us with the challenge of not only do we have to get sufficient solar power generation, but we also need to have sufficient battery capacity to take us through events, particularly at night where we don't have solar power. In contrast, the electronic rain gauge draws very little power. So next slide. This is just costs. Again, I think I went through this. We're demoing here in our office a very small solar panel. In contrast, you'd probably want at least 200 to 300 watts of solar panel generating capacity. Budget $500 to $600 for that. You'll want a good quality solar charge controller. Those run about $230. The solar panel mount is important, particularly if you have a windy site, and those can run several $100s. Budget maybe $25 to $50 for miscellaneous wiring and circuit breakers. And then one of the significant and ongoing costs of a DC power system is your batteries. You need good quality batteries. You probably expect to replace them at a minimum once every 5 years. And we'll talk about this later, that as batteries age, when you hook them in series or parallel, they tend to go to the weakest link. So your weakest battery tends to define the capacity of your system. So budget $200 to $300 for each battery change about once every 5 years. Next slide, please. Battery configurations. If you're solely outdoors, if you don't have any kind of field shelter, we do recommend the absorbed glass mat. That will be most of you, AGM. They are billed as no maintenance. That's not strictly true, but they are resistant to freezing. We recommend deep cycle or also called marine batteries. There's the Optima Yellow series. That's kind of the upper end of costs. Those tend to be $200 to $300 a piece. Or EverStart Max, which are commonly available at Walmart. Those are maybe $75 to $100 US each. We would recommend 2 to 3 approximately 90 amp hour batteries as a minimum to start with. Next, please. For cost basis, if you have some sort of insulated field shelter, we do recommend flooded lead acid batteries. They offer significantly more capacity at a much lower cost. However, they must be protected for freezing. So southern sites, they'd be fine if freezing is not an issue at your site, and you must regularly check the water levels. That would be every few months you'd want to check the water levels. So various configurations are possible. We have some wiring diagrams up ahead. You can wire multiple 12-volt batteries in parallel or connect 6 or 12-volt batteries together. Next slide, please. This is a photo on the left of one of our stations in West Virginia that was recently rewired. You can see it uses 3 12-volt batteries wired in, that's an error, that should be parallel. We have an error on that slide. It should say deep cycle battery bank, 3 12-volt batteries wired in parallel. Parallel meaning that all the negative leads are together and all the positive leads are together, as seen on the right. You can see the diagram. Just a bit that we highlighted at first, some safety things. We do recommend an inline switch that you can disconnect them. Yes, this is low voltage, it's easy to handle, but those batteries have an appreciable capacity. If you get a short, you will quickly melt wiring. You could quickly even have a small electrical fire. So even though 12 volts, you think it's safe to handle, you would want some kind of inline fuse in case of shorting. And along the red line, you can see that to the right, fusing. And then we would want would recommend grounding of the negative side. And that would be for general equipment protection and also protection if there was a lightning strike. Next slide, please. This is another possible configuration. The system operates at 12 volts. What we're showing here is a bank of 4 6-volt batteries. The photo is on the left. This is actually our configuration at our field site operated by the University of Illinois here. So these are golf cart batteries. They're very inexpensive for the capacity. So there's 2 batteries wired in series. So that brings us up to 12 volts because 6 plus 6 is 12. And then you can see they're run in parallel. So that's actually brings the extra capacity there. Again, note the inline switch, fusing, and the ground. Next slide, please. This is just an overall schematic of how the collector would operate. This is just showing if you had line power, how you can operate the ACM collector on a 12-volt battery for backup. So Jeffrey talked about this before we got interrupted, that you can feed the collector with 120-volt inline AC power, and then it also not only trickle charges the 12-volt DC battery, but you can also operate the equipment on 12 volts. Next slide, please. For today's presentation, we're primarily going to be focusing on solely DC powered systems. Next, please. This is an overall schematic of a hypothetical station. It's also what we have mocked up here in our office. You have feed from a solar panel through a regulator that has a blocking diode. We'll talk in a minute about what that does. And then it goes to 1 or more 12-volt deep cycle batteries that are sized in capacity to what you might need in your site. You have an inline fuse holder, and then you actually feed the collector. And let's switch over to our live view. Jeffrey's here. We zoom out a little bit, maybe. And my camera is lagging.
What we really want you to see is kind of, as Chris explained, is a mock-up that we put together. This isn't an actual collector, but it's all the components that would be on the collector and how we went about wiring them in different schematics and the importance of each component throughout the wiring system to have a good functional and safe solar setup.
Let's just talk about each of the components here. Gosh, we are having technical issues. I'm just going to point to them, and okay, now I'm back. Use my lead of my electrical meter. There I am, the ghost hand coming in from the side. So behind us, we have a solar panel here. We've got a little sunbeam we'll turn on in a minute that's simulating sunlight. It's wired into our charge controller here, and we'll have a close-up of it in a minute to show the different connections. That has multiple leads, so there's the solar panel input lead, there's a connection to our 12-volt battery, and then a separate connection to what's called load on the solar controller that has the powering the actual collector. So a few things to note. I'm not showing the ground here, but we have fusing at the collector. There's the built-in cartridge fuse there, and we have an inline fuse for the battery. And we'll talk a bit about how we do troubleshooting there. So let's go back to the PowerPoint presentation, if we could, please. Okay, this is a close-up of the solar charge controller. It's a picture of the one I actually just showed you, and you can see the various leads there. The first on the left with a little sunbeam is the solar panel, so it hooks directly to the solar panel. In the middle, we have our connection to the battery with a note that there is a fuse on the positive lead. The one on the right goes to the NADP collector, which is fused. The manufacturer does recommend grounding of the negative leads, and see their instructions for further guidelines there. Next slide, please. So we'll talk a bit about the purpose of a regulator, because it's important as we do checks, and we can talk about some of the issues that come up. At full sun, we don't have that here in our office studio, but the panels can produce over 20 volts DC, and that would just essentially fry your battery. It's far more than your battery can handle, because it's above the charge voltage that your battery requires. The other thing it does, so not only regulating power that goes into your battery, it has what's called a blocking diode. What a diode does is it restricts the power. It's like a one-way gate. So power can flow one way, in this case, from the solar panel into the battery, but it doesn't let it go in reverse. And the reason we do that is if we didn't have it at night, your battery would discharge through your solar panel. So what this allows it to, what the regulator does is allows power to go one way from the panel into your battery and doesn't let it go into reverse. And these two things can fail. So the reason we talk about this is your regulator may not be regulating the power properly. Perhaps there was a surge due to a close lightning strike. And also the blocking diode can also fail. They do, after a number of years, 10 to 15 years, they are a part that does tend to fail over time, so we'll want to check that. And then I'm going to show you, this is just a description of a check we're going to do. So first we're going to check the blocking diode. So we will show how we check the diode on the regulator. And then the next, we're going to show how we check the charge controller. So we'll be disconnecting the panel, disconnecting the battery, and show how those work. So let's go back to the live view, please. So what I have here is a standard multimeter. This is one we provide to stations. If you need one, we'll send you one. We have a previous webinar that talks about their use, how to configure them there. So let me start from we'll just assume the basic here. So there is a controller that picks the function of the meter. There's the leads that we put in, and then there's an on-off switch. I'm just going to show you how I'm going to configure it for this particular check. If you need more information about multimeter use, I'd refer you to the webinar we did previously on that. So there's a red and a black lead. The black goes to the common. On the front, that happens to be the bottom here. And then you want to check carefully. The top one is for checking amps. The middle one is for showing volts. We'll be checking volts here. So I plug the red into there. I'm checking DC voltage. So that's in this quadrant up here. The system operates at 12 volts. I'm going to set this at the 20 volts mark. And then lastly, I'll turn it on. And of course, my helpful computer just blanked out again. This is day of technical issues. Okay, so first we're going to check the blocking diode.
I will hold this so you can see that when Chris puts the leads to each particular component on the control charger, you can see how it varies.
Okay, so the blocking diode, as you'll recall, normally the power is coming in from the panel and out into the battery, and the blocking diode is the gate to keep power from going in reverse. So what we're going to do is we're going to disconnect. I'm doing this under the table. I'm just going to unplug our solar power lead, and I'm going to be checking for the presence of voltage at the solar power lead. And it should stay 0 or very low. And then for the check, it's again black to black, red to red. And we can see that it's at 0 power. Just for verification, I'll show the lead at the battery. We can see that's reading, it's just slightly off camera, move over to my way. Okay. Yep, we can see that's reading about 13 volts. That's coming through. We will also get 13 volts at the regulator where it's hooked in, but we can see out to the solar panel it's 0. So that tells us that the blocking diode is working successfully. It's preventing the reverse flow of power. The next check we're going to do is checking the regulation of the regulator. We're going to bring the sun out, turn on our sunbeam, because we don't get enough power here. Actually, we could show that. We'll start with a cloudy day. And the nice thing about DC is if you happen to hook up reverse, it just shows the negative. So we can see the meter. I actually have those in reverse. No harm done. Just under the ambient light in our office here, we are producing about 1.8 volts straight out of the solar panel. When the sun comes out, we turn the light on the solar panel behind us, we can see the voltage climbs up. We're about 2.5 volts. If we were in full sun, unregulated, we'd be about 20 volts here. So it's above the capacity of our battery to take it. I'm going to go ahead and reconnect the solar panel into our regulator. And what I'm going to check is first the lead into the battery. It's 13 volts, what we'd measured before. If the regulator wasn't working properly, we'd see far above that. You'd see probably 18, 19, 20 volts. The other thing we can check is the load center, what's going to the collector, and that's also about 13 volts.
As Chris mentioned, though, with the blocking diode, the one thing you do not want to see when you hook these up is to watch your power go down. That's a possibility that the diode could be leaking the power. Mm-hmm. Yes. And that's where you run into problems with the solar panel not being able to consistently regulate the amount of voltage to go through all the way to the not only batteries but to the collector as well.
And then we'd mentioned the inline fuse. You know, you may also want to troubleshoot your system. So if you're not getting voltage here at the regulator, you know, you may want to go back and check at the actual battery because perhaps your inline fuse has gone bad. I should mention at this point, this is a cartridge fuse. You know, a couple configurations are possible. Just a simple cartridge that can pop out, similar to that you find on the Aerochem collector. There's also just a demo, many things for convenience. Use inline cartridge fuses like this one. It's similar to, if I can get it open, similar to an automotive fuse that's just inline there. So it's always good to know a bit about your system and troubleshoot it based on your configuration.
One of the things we'll also talk about as we progress, though, is we want to always make sure that you get the recommended fuses and wiring as far as, you know, being able to just to go out and grab it. Say I replaced a fuse, you want to do it specifically to what is required for the system to operate at peak efficiency.
Okay, good. I think at this point we'll go back to the PowerPoint, please, unless there's anything else you want to mention while we're live, Jeffrey.
Nope. talking about troubleshooting some common issues that can happen with the system. Troubleshooting insufficient solar power generation. You're going to run into this a lot. Obviously, if you have a solar site that's in southern Florida, you have the 80 degrees and 90 degrees and the sun all year round. Your solar panel will operate at peak efficiency. If you're in the mountains of Colorado, where you only see about 7 hours of daylight and most of the time it's snowing, gray and cloudy, then you're going to run into some difficulties. That's why when they the recommendation for optimizing the maximum amount of solar power, how many panels you're going to have, how many batteries, taking into consideration that this whole system is going to operate on the amount of sunlight provided. And you can see where the difference would be between a Florida site and a Colorado site. As Chris mentioned in one of the other ones, old worn out batteries, it's recommended that every 6 months, I say coming out of winter and before going into winter, that you take your batteries and have them load tested. Your system is only going to operate to the capacity of the worst battery within the system. So if you've got, say, 2 good batteries and you got one that won't pass a load test, that system will run only as well as that worst battery. As I said, insufficient battery capacity. If you try to put together a system with the less than the 90 amps that are recommended, and you've got the solar capacity, but yet you've got weaker, smaller batteries to try to save yourself some money, they will not be able to hold the amperage necessary for keeping this system running. So you want to match up what you got coming out of your panels with what you got going into your batteries. Damaged wiring or equipment issues. If you have a motor box or problem or something along those lines, wires, you get mice, you get power surges if everything is done right. When we ask you to check something along the lines like this, if you're involved in a solar site, have you start at obviously the panel and work your way all the way through. Batteries that go low and stuff like that can cause the problems at the equipment end, so that's why we always want to start at the main source, which is the panel. Next slide, please.
I just add one last thing on the wiring. You can think every connection is a way to, you're trying to conserve energy here because you're limited. So check each connection too. I mean, a lot of these low voltage things, you think, well, it's safe. I can just kind of wire tape things together. Make sure all your connections are good and sound. Just because it's low voltage doesn't necessarily mean, make sure your wiring should be good and of good capacity, because that's just wasting energy that you have very little. You need to have good quality cables and connections everywhere. Yeah, sorry, go ahead, Brian. Something, and Jeffrey can chime in here, when you submit your data, and this is if you have an electronic rain gauge, one of the nice things that we have in our setup is the data logger is constantly logging the voltage that's coming out of your collector, and it should be wired that way. If it's not, if you're not seeing a voltage signal when you look at the data, and this is off the website at the top, this is, and you're encouraged to look at the precipitation data, where we actually have a note in the mailing that's coming out with the July data about how to get to this website. If we didn't do it, maybe we did it last month.
We did it.
Yeah, we did it recently, that talks about diagnostics. This is just some graphs that Brian pulled up from one of our sites, just showing the voltage over time. And you can see, probably with some sort of event, the top one, the voltage is dipping. So when the collector is consuming power, it's causing the line voltage, that would be the DC power. This is a solar powered site, to dip. The bottom line is very disconcerting because the top one, it's dipping, but it's coming back up again. The bottom one, you can see, especially with long precipitation events, the line's power is dipping and it's not coming up again. So at the higher mode is probably when the sun's out. The low mode is where, especially overnight, if you look like Saturday and Sunday, where we're not getting enough solar generation capacity, that the voltage is dipping down, and it probably might indicate some sort of battery capacity issue. Anything you want to add, Jeffrey?
Just if you do look at this particular website, you're going to see it in numbers as well. If you need a clarification, you'll see a couple of columns that are right next to the exposures and stuff like that, minimum voltage and maximum voltage. So if you need clarification, don't hesitate to give us a holler or email, and we'll try to clarify what those numbers actually mean.
And we have contact information at the end of the presentation. Let's go on. Good. Now we're going to talk about some maintenance here, and Jeffrey already highlighted this, that seasonally, if you have a flooded lead acid battery, you'll want to check the water levels. Many batteries, I think, have a little sighting in the top that shows the general condition. And then periodically check your battery box. You know, insects and rodents just love to live in there. It's a little bit warm, so insects can damage the wiring, as well as rodents can, obviously, too. Annually, you'll want to load test all your batteries. We've got some pictures just showing what this means. Many places like AutoZone will do it for free, but we'd recommend either, if you don't have one on site, to get a load tester, take them to a local place that would test them. Clean and tighten your wiring connections. It looks for corrosion in that. Make sure they're always clean and tight. And then depending on your equipment, you can balance the battery bank, and that has to do with rotating the batteries. It's a little bit beyond the scope of this presentation, but we can provide further guidance about that, or resources that can talk about that. Next slide, please. Weekly with the sample change, obviously the best check is the equipment operating. You know, note the collector. Is it opening it with good speed, or is it kind of grinding along a little slow, indicating that the battery voltage might be a little low? Is the sensor heating, particularly in winter? Is it warm when you're in cold weather? Is the sensor feel warm to the touch such that it would melt snow? Can you put a little bit of snow on it that it would melt there? I know it's asking a lot to have solar power at northern stations, but we have had them. I think even Alaska we've operated solar.
We've got one in Colorado that's at about a 10,000 foot elevation.
Yeah, we have about actually something we should talk to the beginning, about 20% of our network is on DC. And obviously remove snow. Clean your panels, remove snow. If there's any snow on it, they're not going to be generating any power. Monthly, we would recommend, take some of your DI water or even window cleaner. Obviously, keep it away from your collector, but get those solar panels clean. If there's a lot of debris on them, insects, bird droppings, the like. And monthly, we'd also check, verify the solar controller operation. And that doesn't have to be as in-depth as we showed today with the voltmeter. The one here has some nice LED diagnostics. So there's a green light showing that it's charging, and there's lights showing the battery condition. So weekly or monthly, just generally check, is the controller appear to be operating. Next, please. Load testing the batteries. This is important for ongoing site maintenance. So you do need to disconnect each battery independently. If you have them wired in parallel, as we talked about, you could disconnect them and leave the others connected to the equipment, but you do need to independently load test them. You don't want to do load testing across the entire bank. You want to do it on each individual battery. As it was noted there, if any battery is bad, we recommend that one thing you can do is, if it's testing bad, you could attempt to take it back to your office or your shop and use a battery charger to see if it will take a charge. Maybe sometimes it's just not getting enough charge in the field. We do recommend it to be load tested, because if it does fail load testing, even after manual charging on line power, it's just going to weaken your overall system. It's not it's not really contributing anything if it's failing load testing. There's a note there: portable load testers can be bought for about $50. It is good to have. It's probably not as good as one you'll find at a AutoZone or something like that, but it is good for on-site diagnostics. Next slide, please. And then this is just showing how you could load test. This is one Jeffrey in our office here just shows how to hook it up to the battery terminals, and then it's just a simple, basically straightforward. They have pretty clear instructions. Anything you want to add?
No, just make sure that, as you were talking about batteries going bad, if one's going bad, then the other two probably aren't far behind. Most sites will get into a maintenance schedule to where, instead of fighting and trying to determine which one is bad, to maybe replace two of them, all three of them, whatever you have in your bank of batteries on an annual basis, just to alleviate the problems. And that's if it's within your budget.
Yeah, next slide, please. Just in review, just some things to be aware of. These are photos that come in from EEMS, our site survey team, highlighting. You can see these aren't snakes across the ground of different color. They're actually, looks like multiple wires spliced together. Each of these connections is wasting energy. Try to use continuous wire. Make sure it's sized properly. Make sure all your connections are good. Any the little bundle of electrical tape there isn't going to cut it. Get a little moisture in there, it's just going to leak power, and that's not going to work well.
Most of everything of what we recommend is if you're going to do something along the lines where you don't have the capability of putting it below ground, try to put it conduit to keep it dry and away from the rodents munching on it.
Rodents love to munch on wiring. Yes. Next, please. And then this is on line power, but you can see, this is slammed in the door of a shelter. Again, just keep your wiring good, run it in conduit if you can. Just because it's low voltage, this isn't like Christmas lights you can string anywhere. Still use the same precautions and standard you'd use even for line power. Just because it's low voltage, yes, it's safe, but it doesn't mean that it should be substandard. This is a close-up of the inside of one of our electronic rain gauges, the ETI in particular. It has a separate onboard battery. You can see the terminal on the left, the red one, we're getting a bit of corrosion there. That leads to inefficiency. Sometimes they'll even get warm to the touch. So there's battery paste you can use to clean those up and to have a good corrosion-free connection. Next. Just in conclusion, we have a couple websites. Some of the material and the recommendations we have is from the Solar Electricity Handbook. It's a really great resource. It's published each year. You can see the website there, solarelectricityhandbook.com. It's got tables of locations in North America that have estimates of how much solar power that you'd get based on season, and really good recommendations on sizing systems, batteries, and also talking about maintenance. And then the bottom link to Northern Arizona Wind and Sun. They have been a great resource. We purchase much of our equipment there. We often refer sites to them. They will work with you to figure out what will be best for your equipment. They know about NADP, so they know about typical setups we provide to stations. And I think next, that's it. Just want to thank you again. Here's the contact information. If you have any questions or comments, we always welcome them via email or phone. And on behalf of NADP, thanks Jeffrey and Brian for putting on today's webinar. Thank you to you for collecting the samples for us. Yes. We got a question coming in. Thanks, Kenny in Toronto. How long does your equipment run on the 90 amp hour batteries without charge? Gosh, it depends on where you are. We actually have stations where the operator brings in batteries each week. And I would say I wouldn't trust a 190. I would think 290 amp hour you could probably do a week with. Yeah. I wouldn't try it with one, but we do have a station that brings them in even by snowmobile in the winter, I think. Yeah, one or maybe two stations. A lot of them will operate kind of, the line power's down for extended periods, so they'll bring in batteries each week. Great. Thanks again.